group. And today we have an interesting panel discussion titled Quantum Computing in Machine Learning, Perspectives from Research and Business. So we host great speakers, great panelists from Zapata Computing, Manuel, Rudolph, and Tamer Elkholy. And this meeting, the presentations and panel discussions will be moderated by me and Dr. Rafael Sotero and Dr. Terrill Frantz from Harrisburg University. So we'll start from a brief just introduction of the Washington Quantum Computing Meetup and also Warsaw Quantum Computing Group, because for some participants, maybe this is the first event from this series that they've joined. And later there will be a presentation given by Tamer and Manuel. And you can post your questions to our speakers on the chat during the presentations. And after each of these two presentations, there will be also time for asking questions for discussions. And at the end, there will be also a Q&A session. So maybe one more important announcement is that this meeting is recorded and will be later available for participants. All right, so the meeting is co-organized by Association Quantum and also by the Quantum AI Foundation, organizing Warsaw Quantum Computing Group meetups. So we also invite you to join our next meeting that will happen on Monday. Our speaker will be Sam Kearney, and the talk is titled Creative Destruction Lab, Quantum Commercialization and Entrepreneurship. And very soon we'll also have next meetings organized jointly by Washington Quantum Computing Meetup, Quantum Association, Quantum AI Foundation. So on 24th of April, so in 2 weeks from now, we'll have quantum machine learning lightning talks. Also sounds very interesting. Later in May, quantum mechanics as source code. Our speaker will be Dr. Tamas Varga from ETH Zurich. Later in May, quantum simulations of many body effects in isoelectronic system. And also in May, on 24th, arithmetic circuits for quantum computing. And if you check the website of Washington Quantum Computing Meetup on meetup.com, you can also see some new events that are already scheduled for May, June or July. So I think that's all. Maybe Terrill or Rafa, do you maybe would like to add something before we start presentations?
Yes, thank you very much, Pawel. Quantum South works with complex optimizations problems, leveraging quantum computing on applications to logistics and to finances. Quantum South was born 2 years ago, 2019, at Universidad de Montevideo, and our team frequently joins Washington Quantum Computing Meetups. So we find here a fermental and stimulating community. So thank you for inviting me today to join this panel as moderator, and I hope we can also join as speakers in the near future. Thank you.
Great, thank you very much. Dr. Terrill, would you like to add something?
Yeah, thanks, pal. As a special treat for everybody in the meetup today, I'd like to announce that I've been working with Deb and somewhat with Helen, of course, on putting together a master's degree incubator program. So I'd like to just give you a 30-second spiel as to what it is. But for the record, I'll put a link to something we will be announcing next week in the chat. And for those of you who are watching the recording, if you just simply Google the term master's degree quantum meetup, you'll be taken to the website where we're rolling out this program. In short, it's for those individuals who want to start to get their game face on and start to look towards a master's degree in quantum computing. And the idea here is that this program will be what we believe will be a application enhancer. If you want to bulk up your application to any one of the 32 master's degree programs in the world and show that you've satisfied all their prerequisite requirements, you know how to program in Python, you know how to, you know, the linear algebra, etc., and you know some classical physics, etc., you know, this program's for you. It's also for those of you, the few out there, there's probably about 80 people starting their master's program in the United States and Canada this fall. So if you're any of those 80 people, I encourage you to take a look at this program. It will, the goal is to beef up your application for a master's degree, as well as those who are already admitted, to put you in a position so that you can hit the ground running when you start your program in the coming months. So anyway, if you're interested in master's degrees, just Google master's degree quantum meetup, and we'll start to have detailed information coming out in the coming days. Thanks.
All right, great. Thank you. Thank you very much, Terrill. Thank you, Rafa, as well. So I think we are ready to start presentations. Maybe just to remind you, if you have any questions during the presentations, please post them on our chat, and we'll ask them later after each of the two presentations. So I will just stop sharing my slides, and yeah, Manuel, Tamer, the Zoom is yours, so feel free to start your presentation. Thank you for being with us today and in accepting our invitation, of course.
You're very welcome. Let me know if you see my screen.
Yes.
Mode. This is.
Yeah, we can see your screen.
Great. Thank you so much. So let me just start by introducing myself, and then Manuel will also introduce himself. So my name is Tamer Elkholy. I'm a quantum solution engineer with Zapata. My background is in physics, and I also have some experience with being a solution engineer in the enterprise software world. I finally came to join the quantum computing world because I really am interested in the potential of it doing great things. So my role as a solution engineer is to interact with Zapata customers on technical issue, try to understand their problems and how our solutions can help them. Okay, Manuel, do you want to introduce yourself?
Yeah, sure. So hello everyone. Thanks for the invitation. I'm Manuel, and I finished my physics master's in Heidelberg in Germany, where I sit right now. Last year, and pretty much directly after my master's, so I had already applied for an internship position as a quantum researcher at Zapata Computing, and by the end of the year, I then transitioned to becoming full-time quantum application scientist at Zapata Computing, where I work in the group of Alejandro Perdomo Otis, and I'm doing quantum application research, like how can we use quantum algorithms, and specifically quantum generative algorithms, as soon as possible and for practical application. And I'm going to share our recent work later today. Yeah, thanks.
Great. So so this is the outline of today. We just had the introductions. I'll talk about a little bit at what we do at Zapata Computing, and then I'll give you, a brief overview of quantum machine learning, and then Manuel will take a deep dive into the handwritten digits paper that he wrote, generating generating these handwritten digits with a quantum device. Okay, so quick intro about Zapata. So Zapata was a startup spun out of Harvard in 2017 out of Alan Asperguzic's group. He is a leader in quantum computing, especially as applied to chemistry.
So the goal of Zapata is to introduce companies to quantum computing today and try to make impact with our customers in terms of, improving, computation of certain, solving certain problems that they have. So how do we do that? We do that with our product Orchestra, which is a quantum-ready workflow engine for enterprise analytics. And we do that also through our services team, professional services, who are, basically quantum computing experts and are, have a great experience, looking at problems and finding the best approach to solving them with quantum algorithms. I'm really, I find it impressive that Zapata has done a lot of engagements with customers, Fortune 500 companies, where we've actually came in and solved problems, improved processes for them, and even made them more ready for when quantum computers are available to make actually big impact. And I'll talk about how we do that shortly. So this is kind of like a big picture view of our company again. So we want to deliver quantum advantage to customers, and we do that with several things that kind of define how we set ourselves apart. So we have a very solidly built platform that's Orchestra, and we have a services team again, which is quantum leaders, and we also have a strong IP portfolio, which we believe will be kind of very important for us going forward, because we're starting now early, and we are building that IP portfolio for when these quantum computers will be able to perform much more than they do today. So the way we want to approach this is basically three pillars. We want to look at problems where we can have business impact. We want to look at problems where we spend a lot of time finding the problems that are technically feasible today. So quantum computing will be disruptive, but it won't change the way data is stored in organizations. So we cannot go at customers and tell them, you have to upload your petabytes of data into Amazon if they are currently in their data centers. So we do want to approach things, understanding customers' starting point. And then finally, we want to exploit, the scientific advantage that we have. We recognize the value of classical solutions, but we know where to enhance them with quantum algorithms. So this is how we kind of, this is the type of problems that we look for when we are engaging with customers. So I've been talking about Orchestra, our platform, and let me talk a little bit more in detail about it. So Orchestra is the greatest thing about Orchestra is that it was it was born out of our group's needs. So while we were trying to solve, Zapata scientists were trying to solve problems, they thought, so we are having to repeat these experiments so many times, and things are a little bit disorganized, and it's hard to do all the data management pieces. So we built this product that has so many advantages in terms of being able to make things scalable and reproducible and repeatable. So we can think of it as when you are using Orchestra, you are using it in three different stages. The first stage is the create stage, is where you are building quantum circuits, for example, and these may be hybrid circuits, using quantum and classical resources. And you may be and Orchestra will then provide you the option of choosing the best of all different platforms. So let's say, for example, you find a very good algorithm that comes with the Qiskit library, but you do want to implement it on, let's say, IonQ's quantum computer, or you want to try you want to use a chemistry library that comes with, that's called Psi4, that's a Python library, and you want to use it in a quantum simulator. So Orchestra allows you to pick and choose from all of these software libraries and resources, and from also the hardware backends, and mix and match them together. And the great thing is that when you build these solutions, you're doing it in a very controlled way, such that you don't have to worry as a user about version control. This package will work with my Python installation. Everything is taken care of for you. So after the create stage, then you pass on your workflow, you create a workflow, and then you pass it on to Orchestra. And so what a workflow is basically a series of steps that, of your analysis. And what Orchestra will do is that, it will implement it on all these kinds of backends, whether you're, Rigetti, IBM, IonQ, Manuel, and they're expanding. And Orchestra will also take care of, parallelizing when possible. And also we've built into it the ability to do these hybrid algorithms where, the quantum processing and the classical processing happen iteratively. So we're going back and forth in a loop. And so that's one of the main strengths of Orchestra, is that, it's able to parallelize all these steps, and when necessary, when possible, and then serialize them when necessary, and also do these iterative hybrid quantum computers. And finally, the last step is to evaluate, and we're able to export the data in a very informative way, in such that not just the result, but how you got to the result. What are the different parameters that you've used? And this is important for reproducibility. So when you want to later work on, reproduce these results, you don't have to go back and try to install the same components. Wonder which library did I use for this, which backend did I use for that. So, and then we're able to export the data in so many different ways, so that you are able to, analyze it with either, if you want to analyze it with a Python on the Jupyter Notebook, or if you want to analyze it with Tableau or Excel, we allow, Orchestra will allow you to do that. So that was just briefly an introduction about Zapata and our capabilities in terms of expertise and also platform. So let's switch now to talking about quantum machine learning. And then the first thing that I want to address is why quantum machine learning. So why can't we just do machine learning? So let me start with just very basic machine learning. I'm sure if people are coming from machine learning here, they're going to be very familiar with this. So as you know, in machine learning, you represent data in this feature space or parameter space, where each data point is each of these points on this space is a data point, and your axis is the features of your data. So let's see if you're Netflix and you want to make an engine for recommendations, you would, your axes would be the year, for example, of the movie, the genre. You can just align them, different genres one after the other, and then maybe the movie length. Let's say, whatever parameters your movies are. If you're looking at images, like we'll see Manuel describing his research, so your features now are maybe pixels. So pixel 1 is one axis, pixel 2, pixel 3. And though each point of these is a different image, right? So you can easily see here that, let's say, if you're talking about an image, you have much more than 3 pixels. So your space is going to very quickly become a very large space. So more features means more dimensions. And so, so one thing that once you look at, things this way, you can imagine that it would be very useful for you to be able to describe this data cloud of data points as kind of like a density, probability distribution. So it would be very useful if you had a function that you can just call, and then it gives you a point in that space depending on the probability of your distribution here. And that's the task that is called. So that's the task that's called generative modeling. So so quantum computers, it turns out, they are able to do this better than classical computers. So there are some research studies that show that when you're trying to model the data, there's some quantum machine learning algorithms have better ability to find different, extend to different areas of that very complex feature space. So that's one thing. And then the other thing is that if you want to sample from, so a known distribution versus, like, in the first case we were talking about distributions that come from data, but if you want to sample from a known distribution, let's say that is coming from a quantum circuit, these quantum supremacy experiments that we have, two of them so far, one by Google and one by researchers in China. We have shown that quantum computers are able to sample better from these distributions. So these are two, ways where we can see that quantum computers deal better with these very high dimensional probability distribution. They can sample better from them. They can model them better. Okay. So generative models is this case when you have this probability distribution encoded in your quantum computer and you want to generate new data from it. And then it turns out that this task is very difficult to implement classically, but in a quantum computer, it turns out that this task is more easily done. And the application for that are many. So from anomaly detection, so that you can think of, once you have a good understanding of your probability distribution, that function that describes the data, if you see something that's different, it's easier to tell it apart. Generating missing data from images, for example, and video, and autonomous driving. So there's another approach to, well, another completely different approach to quantum machine learning, which I won't really talk about as much in this talk, and which is the ability of mapping your problem to the Hilbert space. So the Hilbert space is that is the description that's used to describe anything quantum mechanic. So when you have a bunch of qubits in your quantum machine, they are described by a Hilbert space. That Hilbert space has a very large dimension because it grows exponentially with the number of your qubits. So so in the same way that you can do the Cornell trick in machine learning algorithms by expanding the dimensionality of your feature space, you can do the same thing by mapping your problem, your machine learning problem, onto the Hilbert space. And there's been a lot of work done in that area. In that case, this applies more to classification and clustering problems. But at Zapata, we've really more focused on the generative problems that I've talked about in the previous slide. Okay, now, so let me switch over to more of a business argument for why companies should be starting to implement or study these strategies from now. So and then the anecdote is always the early adopters of AI and machine learning because that's the most recent, new innovation, maybe within the last 10 years. So it's, the early adopters of AI and machine learning, there's an article in Business Insider which kind of studied that, 82% of those who were early adopters were able to increase their bottom lines by up to 5%. So there's always an argument for early adoption because, first of all, you gain into understanding into this new disruptive innovation. You start building IP. You start, understanding it better. Even like today, we can go to a customer and do resource estimation, and they get a better understanding of, okay, to solve this particular problem, we need this many qubits, we need this particular quality of qubits, and it would take, a certain amount of time, right? So when a company has this knowledge, they can very easily keep track of what's coming in terms of hardware. So we have, for example, the IBM roadmap, which is telling us amazing thing, right? It's telling us that in 2 years there's going to be 1,000 qubit quantum computer. So you, as a company, when you approach these problems early on, you've built your knowledge, you've built your IPs, and sometimes even in the case, especially for example, in the case of machine learning, they have been quantum-inspired algorithms that came out of thinking about problems in a quantum way. So that's kind of like our approach at Zapata, is that there's a lot of output today that comes from engaging in problems in quantum machine learning, or in quantum computing in general, especially in quantum machine learning. So how do we do that now in terms of getting some use out of today's computer? So our main approach we found is that the hybrid quantum classical algorithms is the best way for us to learn. So these, or to make an impact even. So these are quantum, and these are algorithms which have an interaction between classical processes, classical computing processes, and quantum computing processes. And the way you can picture it here is that it's a workflow where we find the area of the classical computing that is that we can improve the most and replace it with a quantum component. And in that case, in order to do that, there's a lot of pre-processing of the data in order to feed it into the quantum algorithm, and post-processing of what comes out of the quantum piece. And to do that, and so this picture here is also a loop. You can think of this as a loop where, there's a lot of back and forth between the classical part and the quantum part. And so we've been able to develop a lot of technology and knowledge around this. So how do you do that? When you start thinking about the problem this way, there's a lot of challenges that start appearing. You start thinking about framework compatibility. So we need to integrate, like I was saying earlier, all of these different hardware components. We need to be able to deploy it in such a way that we will be able to use the customer's data. And we need to take care of that, all the data flow that's happening. That's the data management part, and the reproducibility, like I was talking about earlier, in terms of keeping track of how we got these results, where they, all the different meta parameters, such that we can easily reproduce the same result when we want to. So the solution to all these challenges is to have a very good software engineering that knows how to make these components and make them modular, scalable, and reproducible. And so all of these qualities are, very important in any scalable enterprise software solution. And we have that, we have spent a lot of effort at Zapata to kind of build those aspects as well as the quantum knowledge. So let me give you an example of what I mean here. So this is, for example, a workflow, you know, a description of a workflow of the variational quantum eigensolver. It's one of these hybrid quantum classical algorithms where there is so many different parts. Each box of these is a process, and there's a lot of data passing from one process to the other, as shown by these arrows. So what is interesting to know is that all this green part here is classical. So you really have to be very good at building large scalable software solution that, you know, can scale with the amount of data that is going to be coming in and out of these different pieces, and it's going to be modular as well. And it's only this part that's the quantum hardware or the quantum inspired piece. And so and so what we've gotten good at is, you know, identifying which piece of the where we can insert. So, for example, in the case of a machine learning problem, especially in the case of these generative models, where can we insert this small, you know, part, which is quantum, which is going to highly improve the classical algorithm. And Manuel will talk more in details about that as related to his paper. And so another example of this is our approach to our quantum enhanced optimization algorithm, QEO in short. So in QEO, we looked at the problem of, you know, okay, I'm going to describe it to you from an application point of view. So we looked at the problem of the S&P 500, looking at the S&P 500 and finding what's the best portfolio that we can build out of these stocks, right? So it's a portfolio optimization problem, and a portfolio optimization problem is an optimization problem. So in an optimization problem, you travel that feature space, try and minimize a cost function. And so you can see, and then there's so many different ways to optimize classically, and, you know, because there's so many different optimizers that you can use. So in this case here, we've taken the results from an optimized portfolio that we've optimized using a normal classical optimizer, and that's the blue data here. And so what this is plotting is, you know, the cost function on the x-axis and the number of portfolios with that cost function, right? So the lower the cost function, the better your portfolio. In terms of it maximizes the return and lowers the risk. So when you do that with a classical optimizer, you get this blue distribution here. And so what we do is then we take that blue distribution, these are points in your feature space, and then with different cost values for each point. And then you give it into you feed it to a generative model, you know, run with as a quantum inspired model. And in this case, what quantum inspired model will do is that it will learn this distribution and look for data points that are similar to these original data points from the blue distribution. So this is the idea of generating generative models. They generate data that are similar to the ones you feed them. So once you build this model of your probability distribution, you're able to create new data points from that distribution. And it turns out that when you do that, this is the orange distribution that comes out. You find new points, new portfolios, which are better, which have lower cost function. In this case, it's risk. So it has lower risk for a given revenue. So optimization is, of course, you know, ubiquitous. It's you can find it in so many different use cases, whether it's biopharma, chemistry, protein folding, for example, routing, that's another in logistics, and finance analysis like this one here. So this is my brief overview of quantum machine learning. And in the next part, Manuel will talk about the paper. A very, I give you a very detailed description of what he's done with this generative model approach. But so I'm happy to take now questions before we get to that second part.
Great, thank you. Thank you very much, Tamer. That was really great. All right, I saw that there is at least one question on our chat that can be just named question number 0. There was a question whether the slides will be available later. So for sure, this meeting is recorded, so the recording will be available for sure. But regarding slides, I believe that if Tamer and Manuel agree, then Helen can also upload the slides on the events website, so we can discuss later.
I think we can make them available. Yeah.
Okay, great, fantastic. All right, great. That was very interesting. And regarding the applications in machine learning, maybe I will just ask the first question. So you said that you are primarily interested in some generative models, for example, and one of the possible interesting applications of quantum computing is to sampling from some difficult distributions, some distributions that might be difficult to approximate for classical computers. And one of the examples was the distribution that was used in the supremacy experiments, quantum supremacy experiments, which is boson sampling. But are you maybe aware, based on the experience that you already have in Zapata, what are some other probability distributions that might be particularly interesting for machine learning that are currently difficult to approximate for classical computers, but for which quantum computers can give an advantage potentially?
So there has been a lot of work that we've done where we've tried to solve these. There's two different kinds of distribution that when we're talking about here. The quantum supremacy experiment is a certain data distribution, is a certain probability distribution. It doesn't come from data. It doesn't come from you trying to fit the data. It just comes from the way the quantum circuit is set up. So that's one way, one place where we've seen the quantum computers do it better than classical. And then the other place is like these, when you have data, classical data in this case, for your machine learning problem, and you're trying to fit it. And then in that case, we did see it in several examples where you can see that the expressibility of your quantum model is better. There are several papers that I can't think of at the top of my head right now, but maybe Manuel, you can think of something you're aware of one of them.
Yeah, so I can probably also jump in. So there, I think we need to make a distinction between like at least 3 things. Like one is quantum supremacy, where the problem itself was constructed in such a way that quantum computers they were expected to outperform given enough qubits and given enough fidelity, right? So this isn't really a practical problem. I guess the question was very much like practically oriented, like what are practical distributions? And the thing is, we don't know, right? There are papers who show a theoretical gap in terms of expressibility of quantum neural networks compared to classical neural networks, right? But these theoretical bounds, they don't just hold always in every practical case, right? So they are like a very general mathematical description of the models that you have available. Now, how this actually ends up in practice is something that is very unclear, and I couldn't say specifically which kinds of distributions are hard, but there are constructed difficult distributions, just like the quantum supremacy was a construction. constructed distributions where you can have a provable gap. In practice, no one has really found yet where like quantum is just like slotted in and it's just like straight up better. Like there is no discussion anymore about this like practical application. So this isn't the case yet. So I couldn't say like which kind of distributions are generally better quantum.
Great, thank you. Thank you very much for the answer. So yeah, I think we can start reading the questions from participants, but maybe Rafa or Professor Terrill
Yes.
would like to ask some questions. Yes, Rafa.
Yes,
Go on.
Pawel. I will start with the questions in the chat. Okay.
Yes, go on.
So there is one question that maybe many of us are also wondering. That is for Tamer. When do you anticipate hybrid-based models like, for example, variational methods like UA-OA to become relevant to solve important industrial problems like route planning more accurately and faster and at a larger scale than classical techniques?
I don't think anyone can give a date, but I think these. So what I haven't also mentioned is some of our algorithms as well. They are even the variational algorithm. No, sorry, not. So some of our algorithms and some of our way of processing, quantum data, for example, looking at measurements and trying to, squeeze the most out of them, they apply to even, fault-tolerant quantum computer. So the idea is to build knowledge that will help you, throughout that transition between the noisy and the fault-tolerant regime. Now, when will the fault-tolerant regime come? It's not really clear, but it's really, really encouraging to look at, the roadmaps of hardware manufacturers, and the one that, off the top of my head, is the IBM one, where they actually are planning to have a 1,000 qubit in just a couple of years. So if you think that you're going to have, if you think about it, you're going to have a 1,000 qubit machine, maybe not fault tolerant, maybe not very low noise, but you're going to have that in just a couple of years, and then that will greatly expand your capability. So what about 4 years from now? What about 10 years from now? So.
Okay, so that machine about expected to be in 2 years with 1,000 qubits. Still, I mean, in this slide you have, you are showing, you are talking about great problems and billionaire problems, protein folding and routing, last mile delivery, and financial analysis. So with 1,000 qubits, what would be the size of the problems that can be addressed?
Okay, well, as you can see from the slide as well, we've already taken a quantum-inspired method and then run it on I guess a 500 data point. This is so we have 500 stock from which you can choose, right? So we have a very big space to explore. And then we've been able to kind of find better solutions with this approach. And then, as you'll see in Manuel's presentation, that's even better, because we are only replacing a small part of the classical algorithm. So another way to look at it is actually to think about error correction as well. And if you have 1,000 physical qubit, I'm not sure if you want to create much better logical qubits, you have to kind of like group them in terms of the number of qubits that that you can do error correction on. So, and in that case, I'm not really sure how many physical qubits you may need for a logical qubit. There are some codes that require maybe 10 or 9 or something like that. And I'm not sure how much of an effort, how much of an improvement that's going to give you. But if you start to think of it, even if you had, the simplest codes give you, maybe it will require 9 physical qubits to make 1 logical qubit. And in that case, you get an order, an order of magnitude lower. So from 1,000, you go to 100 logical qubits. So maybe even with 100, maybe if you have 100 logical qubits, your Hilbert space is huge. So perhaps that's one way to think about it. Maybe that's not going to be the case because the errors are going to be larger than you can apply just a 10 qubit error code correction algorithm. But yeah, it's really hard to tell. But I think the point is the hardware is improving very fast, and so I think the algorithms also have to be ready for when the hardware is ready.
Thank you. So there is another question more related to the software technology, and says, how does Zapata Computing's quantum machine learning software compare with IBM's new QML library release?
So let's see. I'm trying to think of what is public and what is not yet disclosed. But I think we've done a lot of work on QML so we have a lot of expertise, and we do all of our work using Orchestra, and so we have this platform that's ready to be improved with all of these pieces that are going to be solving all different kinds of problems, including QML. So I think the best way to answer this is to look at our results. For example, this QEO paper and the paper that Manuel will talk about.
Okay, sure. Manuel will talk about a very interesting application and with very interesting results. So I have one more question, Pawel. I don't know if I have a little time yet. Yes.
Yes, we still have time.
Okay.
So go on.
So this is a higher level question about your introduction about Zapata. I am interested about quantum computing entrepreneurship, and Zapata is a great example. And but for new incomers, I mean new startups that maybe might be starting up in these years, what Zapata may be an example. And I would like to know about what is the business model now in these early years. I mean, if the business model is, for example, you mentioned your work with Fortune 500 companies, and is that consultancy or is that joint collaboration to get in touch one with each other so Zapata can gain insight on the problems they have, and the companies get advantage of working with Zapata? So is that income source for Zapata, or Zapata is is working based on venture capitals and so on? I mean about the strategy and business model.
No, we are definitely getting into consultancy projects, and we are being paid to give them our quantum computing expertise. So we do solve problems using our quantum computing expertise. For example, the BP project, if you look at the paper that came out, I guess a few months ago, maybe the end of last year, We spent time with BP, and we kind of did a very robust resource estimation for what kind of quantum computers do they need today to solve specific problems, right? So we got together and we worked with them, so that was using our quantum expertise to in a consulting arrangement, and we are also using our platform to kind of share with the customers for them to be able to run their own experiments as well. So I think in our case, we decided that we want to build both the expertise and a very strong platform that companies can use. And I think, and there are different models. There are different quantum computing startups that approach things differently. Maybe some quantum computing companies will think more about the long term, and then and try to build algorithms for the long term. I've met such a company, and there are so many different ways. But I think today, this consultancy model is very relevant, because there's a lot of problems that we want to solve for companies, and there are companies that do want to be ahead of the curve on getting started with a potentially disruptive technology like quantum computing.
Thank you.
Great, thank you. I see there's another relevant question about this quantum startup world. From an ecosystem perspective, do you see any opportunities for software startups to help more people easily explore integrating QML in their classical algorithms, independently on hardware progress? What are the challenges and bottlenecks currently? So it looks that Manuel has already replied. So maybe Manuel would like to just read his reply as well.
Yes, I mean, you can answer this question in so many ways. But the one that instantly came to my mind is one that I'm dealing with on a daily basis, right? So when I try to when I'm testing new or modified quantum algorithms, and I want to see how the performance is with different simulators, thinking about which hardware could this be run on, and so on. If I'm so used by now to just use the code resources by Zapata, inside Orchestra, where I only need to know the language that the Orchestra code speaks, right? And it translates to all different kinds of simulators and hardware providers. Everyone has a different idea of how to speak to the machine, how to speak to the simulator, what's the syntax actually for designing a circuit, and all of that. If you just someone with a Python notebook who wants to try different libraries, this is really a waste of time. And that's the kind of the first bottleneck that came up to that I thought of with regards to the software bottlenecks.
Okay, great, thank you. So in your reply in the chat, there is an interesting. So there's also a summary of the Orchestra tool. In fact, so you said that we try to build interfaces for people to use any software hardware they like. So as Tamer explained in the beginning, right? So potentially, thanks to such interfaces, engineers, researchers can use software like Qiskit from IBM and then run the programs prepared in Qiskit on Rigetti's quantum hardware, right? But an interesting question is, have you maybe analyzed or have you found out that some software models just integrate better with some specific hardware? So for example, I can expect that the software prepared using IBM's technology like Qiskit is probably most suitable for IBM's hardware, but maybe it's not the case. Maybe there are some cases and situations, and maybe you have such an experience that, for example, IBM's software technology can be run more efficiently on, let's say, Rigetti's platform. Are there such cases, or have you experienced something like this?
So I think I think that, I mean, obviously it's easier to use IBM's kind of devices if you're already working with the like Qiskit library, but like actually talking to the devices isn't like it's not like it's completely dependent on the rest of the code. It's just a request to the device with your circuit that you like send to the queue, and then you get results, like, right? So that's the only thing that really goes to the quantum device and comes back. You can do that from any language. All you need is how to translate from any language or like from any library interface that you're using to exactly the language that like the IBM backend speaks. And so all you need is a couple of dedicated software engineers who go around like doing these integrations. And then you're pretty much set. I mean, of course, like updates come, and so like there's sort of upkeeping to be done, but so unless it's something like TensorFlow Quantum, where they actually, where the like quantum circuit simulation and the like neural network integration, they go hand in hand. You have like forwards and backwards passes with the gradients. Like it's really one thing, but usually if it's not like basically one big tensor, like one big computational graph, which everything but TensorFlow pretty much is, then you can single it out pretty well and build interfaces for it, I think.
Great.
Yeah, let me just add something. You can think of the problem in different layers or stacks, the same way we do stacks classically. So the higher level stacks is the circuit, the logical circuit that you can just pass on to different machines, or quantum machines. So and as long as they are using the circuit model, so the circuit can and the algorithm they're the same for everyone. And so you will find in Qiskit's library, for example, different algorithms for different problems, and while they know how to implement them in their own machines, IBM machines, any other hardware manufacturer is able to implement any circuit because they're using the circuit model approach. And so if you find a good algorithm with IBM and you want to implement it in IonQ, that should work, because the middle layer is then made and optimized by that different hardware supplier. So the IonQ people will know how to translate that high-level circuit into their own, pulses, laser pulses onto the ion trap device.
Okay.
So like one further note, like if you have a specific algorithm that is trying to optimize fidelities and readouts, connectivities, like on actual noise models, then you need to, even though you might be talking in a higher level interface language, you might be still very interested in the precise capabilities of the device that you're like eventually going to be running on. So you can't run the same circuit with the same kind of fidelity on two different devices, even though these devices might have comparable like average fidelities. Like certain operations, certain connectivities just have like more or less noise, and so even though it is generally like very possible to switch out just like the devices and simulators, like when it comes really in practice with noisy quantum computers, you still need to configure out the best variation of your quantum circuit for this exact device that you're going to be running on.
Okay, great, fantastic. I can see at least one more question that looks interesting, but the answer should be probably quite obvious. So currently, as you said, this quantum machine learning approach is based or can be run in a hybrid model, and the question was whether it's the best way. So I guess that the idea is whether there might be some quantum only approaches for quantum machine learning without this classical part.
I think for the foreseeable future, it's going to be hybrid. Even in terms of, you know, the data in the end, even the data is classical. So whenever you have a machine learning problem, you know, there are sometimes, maybe in the future, we will want to do that on quantum data, but for all, you know, practical applications, the data is numbers, you know, that come from a certain application, you know, whether you want to generate new data for images. These are, you know, images are classical data. So so far there has to be a classical component, at least even in the data input, or, you know, transferring the data into quantum data. But I think for the foreseeable future, it's going to be mainly like this, you know,
Okay.
hybrid models. But I don't know, Manuel, do you want to add something?
No, sounds good.
Okay, yeah, it sounds good to me as well. So this is what I expected. All right, thanks. I don't see more questions now on chat. Rafa, Terrill, would you like maybe to ask something else just before we start the next presentation?
I have a quick one, if I may.
Yeah, sure.
Unfortunately, you know, personally, I don't get a lot of time to get my hands on the code as much as I passionately desire to. But guys who are in that space, and you know, hopefully the engineers kind of smooth this out. When you're working on problems, do you find yourself living in the quantum world? In the basically, we're in a hybrid environment, right? You got the quantum and you got the classical. You got to work together there. Do you find yourself living in the quantum world and saying, okay, I need to pass something on to the classical world? Or do you see yourselves personally still living in the classical world and say, okay, I need to pass something on to the quantum world? It's a very ambiguous, but hand wavy type of question, but where are you?
Question for Manuel. He's the one who is.
I guess so. Yeah. I mean, so there are algorithms which we study which are purely quantum. So in that sense, it's kind of obviously the quantum world, but still I would think that it's more, I live in the classical world and try to like run certain routines, subroutines, like kind of in the quantum language. So yeah, pretty much that. It's hard. So like any literature that you have on machine learning or like algorithm development of anything of any kind is classical, right? This quantum stuff is very new. And so the only reference that you have, all you know basically is classical. And even though like, I'm a physicist, I still see it as doing something that like is useful classically, but on a quantum computer, right? That could be useful classically. So.
Yeah, I just, you know, when I went through the transitions over the years, we used to have a world where we would write programs using go-to statements, which is probably not even in the vocabulary anymore. But it literally took years to start to get out of that mode of thinking, because that's where I started when I was a kid. And then, you know, object-oriented programming came to be. And it literally takes years oftentimes in some of these transitions to really, really change your mindset. And I was just curious, you know, to really, you know, get the benefits of the new regime, if you will. So I'm just curious. Thanks for that answer.
Yeah. I mean, as long as as I have a classical laptop on my desk, I think it's going to take quite a while to just only think in quantum. Yeah, so sure. Thanks for the question. Very interesting. I guess it's my turn now.
Yes.
And great. So I'm guessing you can see the slide as it's probably intended.
Yes.
Yep, that's it.
Right. So so I'm going to present one of our recent papers with the title "Generation of High-Resolution Handwritten Digits with an Eintracht Quantum Device." And it's a collaboration between some Zapata scientists and INQ. So in this paper was specifically Sonica, and it's our kind of bigger foot in the door when it comes to running quantum algorithms for a practical application. In this case, for generative modeling on a real quantum computer. So yeah, so Tamer like already mentioned like what generative modeling is trying to attempt. I will try it from the perspective that I see it, and kind of build the algorithm from the bottom up. So generative modeling is the field of really understanding and modeling a probability distribution, right? Being able to study it and to generate new instances of that underlying probability distribution. There's a lot of applications, for example, image generation, very popularly, but also molecular discovery, time series simulation, anomaly detection, much more. Now, for image generation, for example, let's take this as an example. There is a famous website called thispersondoesnotexist.com, where 2019, like one of the breakthrough kind of models in generative modeling, the StyleGAN 2, was trained to be able to generate these really high resolution, like extremely impressive images of people that do not exist, in fact, right? So this model was trained on images of people that do exist, was able to understand what the concept is of what is people, right? In this kind of pose, in this kind of lighting. So it's very biased, of course, to the exact training set. And then it's able to generate instances that have nearest neighbors, let's say, in the data that you provided them, but they aren't at all direct matches. In molecular discovery, it's you can imagine similarly that you provide your generative algorithm with molecules that do exist, or with like drugs, right, for medical treatment that exist, and you're trying to model this underlying space, and you're able to generate new drugs designs that are perhaps like more effective, cheaper, like more synthesizable than the ones that you like were aware of. And you can do the same with time series anomaly detections. Always, what is the typical, like, or what does this data generally look like? And then you like fit it into a parameterized form. You're able to kind of manipulate it and also to generate new instances from it. Now, our work is in image generation, as the title of the paper says, and more specifically, it's image generation with a quantum component, with a quantum device. Now, the state of the art of producing handwritten digits from the MNIST data set, so with the MNIST data set of handwritten digits as the training set, that was like in October last year by a Chinese group. And obviously it's lower resolution and only limited to a subset of their full training set. And it was though a full quantum algorithm. Now what we did was a quantum classical hybrid, and which is much more scalable and produces high quality images, and it still allows us to kind of find an advantage in a way. So yes, so I want to like re-emphasize, this is a quantum classical algorithm with one quantum component. And this is also something that Tamer stressed. You have a whole lot of classical stuff going on, which works, right? Like, or I mean, given that it works, right? It works. And then you find the one piece that is the most fit to be replaced and be improved by a quantum device. And that's what you do. Right, so the quantum component that we utilize is the quantum circuit Born machine, and or QCBM, I'm short. It's a slightly complicated name, but I think you will become like more familiar with this pretty easily. So the goal of a QCBM is to encode data inside a quantum wave function, right? So the data in this case, because it's pretty, like if we talk about as here like 4 or 8 or something qubits, data is going to be pretty limited. It will be binary samples, right? So quantum measurements. And in fact, the probability that we model in the wave function is then just defined by the amplitude of this certain binary measurement outcome inside the prepared quantum state. So you have a parameterized ansatz. You tune the parameter such that the wave function is such that when you measure it, the probability of given samples is so that like as you want them. So in it's not very like natural to make this transition from high resolution kind of images with continuous pixel values to this binary space. But this is where quantum is right now, right? And now the wave function, of course, when we prepare it on a quantum computer, isn't just plain text. We can only measure it we can only see it and by measuring it. And so if you have a training set that is this kind of gray underlying distribution over the binary samples S, where PS is like the probability for each sample, you're trying to fit that, right? You're trying to find a parameterized representation of this data inside your quantum circuit. And the interesting thing now is when your quantum circuit is kind of structured in these layers that we have here, so where you have alternating single qubit and entanglement operations, you like more parameters give you more degrees of freedom, and more specifically give you the ability to more flexibly fit distributions. Now the question is like, why would you use quantum? I mean GANs, like these kinds of algorithms that did these beautiful images we just saw, like they work, right? But they aren't perfect. And it's one thing that's very specific about quantum is that they can encode like complicated distributions, which are, let's say, provably, theoretically, they can be outside of reach for classical algorithms, which doesn't always hold in practice, keep that in mind. But we still have a compact generative model that is able to learn complicated distributions, and we're able to efficiently sample it by just measuring it once, right? So this is something that classical models lack. So they are either not very flexible, or they aren't good to sample. And then on top of that, we assume that the QCBM, like these quantum circuit approaches, can generally learn very complicated distributions. So we think that this is pretty promising. Now, when we think about what we have right now, we're only measuring in computational basis, in Z basis. Once you go a step further, and what we did is also utilize measurements in other bases, because that's what makes quantum in a sense, right? It's measurement in different bases. And so what we then do is, apart from just measuring in one basis, we also measure, for example, each qubit in an orthogonal basis, in Y basis, right? This would be this like pi half kind of rotation here that rotates into different bases. And then we have a different set of measurements that isn't the same as before, but it comes from the same learned wave function, right? It's not the same distribution, right? But it's the same wave function. And so it does contain information that we might think is useful. And the kind of the more like meta machine learning approach is then to also train the basis in which you measure, right? So you literally train not only the wave function, but also in which bases you measure to extract the information. Now, this is one approach that we came up with for utilizing what we had on available quantum devices. Like what exactly are the distributions which you can encode with this isn't obvious at all. But we're trying to see how we can make use of it. And so this is our quantum component inside this like overall algorithm, and the classical component, as I hinted at, is a GAN, like it's a generative adversarial network. And I'm just going to assume that you're not very familiar with this algorithm, so I will like rebuild it from the ground up, as I really like to do. So a generative adversarial network is based on adversarial game between, for example, let's say it like in other words, between an art forger and a detective, right? So the goal of the forger is to earn money, which means he has to draw images which are good, which look like art, right? Which is like indistinguishable from real art. Now, in our case, because our paper is called Generation of High Resolution Handwritten Digits, it's hinting that the data set isn't actually like paintings, but it's MNIST images, right? It's handwritten images. At the beginning, the forger is just like still pretty bad, and the detective has an easy time identifying kind of which are real images and which are fake images. But over time, the forger is realizing which are kind of the features that a detective is basing his decision on, right? And he can adapt this and become better over time. And he becomes better at faking these images. And then finally, let's say ideally, right, if it is successful, the fake images from the forger, they look indistinguishable when the game is then played to its fullest conclusion, where it's like stalemate. So this is the fundamental idea behind a GAN, a generative adversarial network. Now in practice, these aren't like people. There isn't really a forger or a detective, but there are artificial neural networks. So the forger, for example, is a classifying network. It's receiving, its job is to receive real training images like from the real world or from your data set, and the generated images from the forger. And it's trained to classify which is real, which is fake. And now the forger, of course, is then also a network. It's a generator network. So like the discriminator consists of several layers of classical, like here convolutional neural network layers. And kind of the last layer has the same number of nodes as the images has pixels. Right? So this is a very successful algorithm that was proposed in 2014. It has grown and been improved tremendously. It's actually absolutely incredible in my mind what has happened in 5-6 years. And so it's an algorithm which has proven to be scalable, right? It can work. You can use it for very different kinds of data. It can be images, it can be time series, it can be 1D, 2D, and it scales well, right? So what is the problem that we identify? It's in this gray noisy box, right? And this is exactly what it is. It's noise. So because what is needed for a classical model to generate different things, right? You need some randomness somewhere. Otherwise, like what is going to produce different kinds of images? So what you usually do is to just literally throw random numbers, like random noise, inside this generator, right? That's the input to the generator. Now, usually you would call this a prior. It's the prior distribution to your entire like probabilistic model, but it's not a prior. It's just random noise. So even though these algorithms are scalable or have been scalable, one of the best models, which isn't exactly a GAN, but one of the best generative models is the GPT-3 language model, from 2019, 20, I think. And it cost at least $5 million to train, right? Just in in the computational resources. It's a fun game to keep scaling, but we're trying to find the component that it's most lacking, improve that, and overall perhaps improve everything. So that's where this multi-basis approach for this QCBM that we had comes in. It's exactly there, right? We have now not a random noise prior, but we have a prior which can be parameterized. It actually models a distribution which should contain information about the entire probability distribution that you're learning. So currently, classically, let's say, all the learning happens in the classical generator network, and all the learning is offset to there. And what we are trying to do is pulling some of the learning back to the most integral, most salient part of the entire algorithm, which is prior. Now, what do we train this on? This is where there's a lot of research to be done, but classically no one is really. It's astonishing. No one is doing this, and I think I'm pretty convinced that it's because first of all, scaling has been working quite well, scaling the networks, but also because classical alternatives in learning smaller, compact generative models, they are lacking. So even though this is a quantum algorithm that we're implementing here as the prior, this could, in theory, be a classical model as well. And this is also one of the philosophies of Zapata, where, yeah, you start thinking like quantumly about stuff, which maybe gives you better ideas how to do it also classically. But in the end, I mean, quantum like this quantum component has a lot of promise, so it's definitely worth exploring. So let's talk about how we train this. Like, what is this prior actually doing? Now, like one thing that you saw here is latent space. And at the beginning of training, latent space is pretty much random. It depends on like how you initialized the network parameters, which means when the data is like passing through the discriminator, what are like the actual activations of the nodes in there? And so this builds a different space. Like each image coming in is like one point in the space. It's pretty much random. And so over time, while the discriminator is becoming better and better at classifying, also the shape of the space is changing. So the discriminator at the end has a representation, a really compact representation of the like data, of like the images that are coming in, because otherwise it wouldn't be able to classify correctly, which is like real, which is fake. And it is pretty successful in doing that. So we know that this small layer of latent space contains information about the training set that is important for classification. And this is what we train on. This is literally what we train our quantum circuit Born machine on. At the beginning, we start with we start pretty much classically. At the beginning, we start classically with random noise. Right, and over time we tune the quantum circuit parameters such that we actually generate from a distribution which looks more like the latent space in the discriminator. So the prior actually contains information which is relevant in this entire algorithm, in this classification process, and of the real data. Now, this is, I must say, this exact algorithm is a heuristic. There isn't a provable reason why this should be the best way of training a prior, but there is no, like, basically no papers for that. Like, no one is doing this, and we will see that it's very promising. So, this is heuristic, and the prior is like actually a bigger component inside its algorithm, is a hyperparameter that you can influence. And our simulations. I'll give you our simulations to start right now, right? And also some visual understanding of what's going on. Now, don't look too much at the curves yet, but what we see here is this plot of Inception Score as a function over the training epochs, over the training iterations. Inception Score is a common method of scoring these generative networks, and it measures how high quality, like how close in kind of appearance are the generated images to the training set images. That's like how good are they, and also how distributed are they, because we don't want just one very nice images, right? So we want good images, but that are representative of the actual data, right? So varied across all different, like all digits between like 0 and 9. In this case specifically. So at epoch 1, the Inception Score is pretty low, but over the iterations, over the epochs, it becomes better and better. It becomes like it learns what the data looks like, and with a maximum of 10, it would be like the theoretical perfect score, but the actual training set doesn't. Even the training set doesn't achieve that because people have bad handwriting. But at the end, we have like very clear outputs. So this is like the general, generally what you would expect when you're training this kind of algorithm. Now let's look closer at the curves. So what you see here is on the left is the average results of our so-called quantum circuit associative adversarial network with 8 qubits in the simulation against a comparable classical GAN or deep convolutional GAN, which doesn't have a parameterized prior. So the entire network is completely the same in all cases that we see here, but only the prior changes. And so this is also something where orchestra really came in, because like you had to, if you keep one thing the same and you just slot out like one small component, you don't want to learn a new language all the time. Like how do you write this prior now, right? So this was very helpful. And what we see now is with 8 qubits and this multi-basis technique, which is better than not using the multi-basis technique, but we achieve the highest average and highest best inception scores, like over many repetitions of this experiment, of the simulation, let's say. Also, I mean, if you have a 16-bit random classical prior, it's like random noise, it's better than 8, right? But it's still better to have 8 qubits, which model the distribution like on a more fundamental level inside the prior. And this algorithm like then outperforms an average with, at the end, it has different trend also, but at the end it outperforms by 1 standard deviation. And after all, like what you in classical machine learning usually care about, which isn't beautiful always, but it's the best result, right? And the best result we got like was in these like quantum simulations. And it is an improvement only by changing the prior by like several percent sometimes, right? So one of like the middling classical GANs compared to a middling quantum GAN, like quantum like prior GAN, this can make percentages of difference even on this data set, which is pretty easy and well understood, let's say. Now we saw promise in this, like we saw this as good results, and we ran this on hardware. We ran this on the IonQ Eintracht quantum computer, and we only did 1 repetition each, but entire training, which means that every quantum circuit that was ever done in these simulations was now run on hardware. So we did 1 repetition each of this trained basis like approach and the fixed basis approach of our quantum circuit, and we take this with a grain of salt because it's just 1 run compared to averages, but the hardware implementation does not underperform compared to simulations, right? So this is something that's very unlike other hardware implementations that we have seen, especially for only like pure quantum algorithm rather than quantum classical ones, where the experiments usually do underperform quite significantly. Now, one of the best kind of inception scores we ever measured was in this 1 quantum experiment. So you might, it is very interesting to do averages and to convince IonQ to let us run like dozens of these experiments, but it's still one of the best inception scores ever got in this 1 run. So I would assume that it's not a complete fluke. And I think that it also makes sense if you think deeper about this algorithm, what the prior is trying to achieve. So this is where this concept of exploration versus exploitation in my mind comes up a lot, because if you have a very specific kind of shape in the prior space, you aren't forcing new examples onto your generator. So it's only going to ever see what it sees right now. It's going to improve that, but it's not going to explore, right? And so this is exploration aspect, which random noise does very well. It's only exploration, basically. And now exploitation would mean that you hone in on a prior subspace, which is very promising, which produces very good results. And now, even though this is on hardware, which is quite noisy, so you would expect that every kind of shape that you really get into your prior space is going to be washed out by noise. And I think it's quite reasonable to assume that in the actual context of this like generative algorithm of the quantum classical one, that some noise and like reasonable like noise floor might even be good, or like not bad, let's say, right? And when we still are able to introduce some significant reshaping and modeling inside the prior space, even with noise. So this can be scaled, right? This can be scaled to other data to explore the effect of this prior modeling in more complicated data sets, and we're certainly going to explore that. Now, to summarize my part, and I think like in my version of what has been like talked about today here, so we can study with these quantum hybrid approaches. We can study the role of quantum resources right now for practical application, but only if we put them into this quantum classical frameworks. Now there is of course a lot of research, a huge amount of research to be done on like purely quantum algorithms, what they actually can do. But still, we can already start testing this for practical application as the more fundamental research improves. And so these quantum classical frameworks allow for the scalability that we need for practical application. And what kind of is our like main point in this paper is that this algorithm specifically and these kinds of algorithms, they can be tested right now on noisy hardware. Right? So you need kind of a contract with one of the hardware providers, sure, but this is like an end-to-end algorithm that was performed on hardware with one of the components being like a quantum component. And this is something that Orchestra, Zapata's platform, supports, like is intended to support and does support. And yeah, I think this is a good place for me to stop, and I'm happy to take questions.
Right. Thank you very much, Manuel. That was very interesting and great. Yeah, it's time for questions. I can see the first questions in our chat. Question from Fernando Hernandez. In order to have the mentioned results, which quantum computer or simulator did your team use? IBM's Microsoft D-Wave. Also in the article is mentioned D-Wave 2000Q, but why not contemplate D-Wave Advantage, which is newer? And the question is also, is your code publicly available?
Okay, I have the chat open. Let me go through this. So,
yeah,
which quantum computers did we? So simulators, we use the like whatever we think is best performant. So simulators, we aren't bound by anything. The quantum computer that we did this experiment on was IonQ's Eintracht quantum computer specifically. So this was ion traps have like knowing the kind of it's well known that they have like better connectivity and like pretty good fidelity, and this is something that our algorithm kind of out of the box just needed. So IonQ was a pretty good choice there. Why not D-Wave? So I personally have never done kind of algorithm development or research for annealing devices. It's something that until very, very recently has kind of fallen out of favor. Also because there isn't kind of the end of the tunnel light which shows a provable gap, right? This is not something that quantum annealing devices have, and all the quantum computing hardware manufacturers, apart from D-Wave, use quantum circuits or like quantum circuit-based hardware. So it's just something that made a lot of sense and has much more, I think, potential to be flexibly slot in and out of algorithms rather than D-Wave. But I'm not an expert in D-Wave devices, so you should not take this too strongly. Yeah.
Okay. There was also a question whether the code is publicly available.
So so this code is obviously an Orchestra, which isn't publicly available. So this is something that I'm pretty sure like Tamer can can lay this out more like correctly, but this is something that is available for partners in active collaboration with Zapata.
Okay. Did you examine another algorithms apart from the GAN and AAN mentioned in the article?
Yes, I mean, I am studying other algorithms than that. Yes.
Okay.
Yeah.
Yeah, so I just maybe extend this question. I have my own question regarding GANs, because you mentioned DC GAN in the paper.
Mm-hmm.
Have you maybe observed, or do you have some experience with some other GAN architectures? Because of course there are some other architectures.
Yeah.
Cycle GAN, style GAN, and my question is, have you maybe observed that for some specific architectures this approach can be better, more successful, more efficient? Or are there, or even more general question, are there any specific attributes, properties of a given GAN architecture that may make this approach successful, let's say?
Yeah, so I mean, also the chemistry example that I gave on the first slide isn't just a GAN, right? So like just plain GAN is already outdated, let's say, as you mentioned. Now I think this exact algorithm, because it's already based on heuristic, where that the latent, like one of the latest layers, the latent space in the discriminator actually encodes salient information. This already assumes that you have such a space of such a size that is in the discriminator, right? And so, like even like for kind of recurrent tasks or something, it's not quite clear what the latent space even is, or in more complicated architectures. So I do think I'm very convinced that that modeling the prior and really studying the prior as a more than valid. It's really like it's a really big thing. Even if it's the smallest part of like a generative model, it's a really big thing. Kind of what you source your like randomness from. I'm really convinced that this is generally something that will improve many, probably any like generative processes. But I'm not sure that this exact kind of associative framework where you track a latent space inside the discriminator is necessarily the one that gives you the most flexibility. I think there are other so I'm also working on other kind of possibilities for this, but I think generally that this is something that we should all more closely think about what we actually do with the prior.
All right, thank you. I can see that there's one more question on our chat. Do you foresee using QC AAN approach for reinforcement learning problems with other risk-reward functions?
Sure. I mean, it again, I think it really comes down what you track with your prior, like what you train your prior on. And if what you train it on kind of resembles what you want to achieve with your like reinforcement learning algorithm or whatever that may be, then I'm convinced that this can help. Yes.
Okay, great. Yeah, I don't see more questions on our chat. So Rafa, Terrill, maybe you have some questions?
I'm good.
Okay. So Manuel, well, I have one question about the multi-basis UCVM. I mean, I'm not familiar with this hardware, and so is this something that was already implemented? I guess it's not something that has a lot of applications yet, or what is the case? Of this
yeah, so this multi-basis technique, this is something that I mean, it sounds weird, but that I came up with. The idea is it's very much not clear to me what exactly are the like full capabilities of using this. So you can imagine that you could, instead of doubling your like space, by measuring again another basis, you could just have another quantum circuit doing that, and kind of in like a patch-wise fashion, like kind of build these product states, like for each n bits that you have in your like output. Then, but these are independent models. So there are algorithms which have this approach where you model this by an entire differently circuit, but here we really assume that the wave function that you learn contains all the information that you train, right? And not just in computational basis, perhaps. So we try to really just get samples from all kinds of bases in order to most kind of representatively use what our wave function, what we have in our wave function available. Now, what this actually is useful for is at plain sight very difficult to say, but I think in combination with a classical neural network, this becomes in a way very beautiful, because these kind of black boxy algorithms, they bank on the fact that they can extract kind of what is present as information, right? And in the underlying correlations between the inputs. So like, even though like kind of the first n and the second n bits of your samples, they are almost in a sense the product state, but they come from the same wave function, and then the classical neural network can like order them and post-process them as it thinks that it's most useful. And so this is something that isn't like provably good, but it's our attempt to make use of the quantum resources most productively in together with a classical neural network.
Thank you.
Right, great. Thank you, Manuel. Thank you, Rafa. Terrill, would you also like to ask some questions? If not, okay.
No.
Yes, we can hear you.
No, I asked the burning question I had earlier,
All right.
Great opportunity to talk to people with their hands in the dough.
Okay, great. So yeah, I don't see more questions on our chat, so maybe I would just ask one last question for today. So most of the work that you described is just based on using quantum computer or quantum computing in general to just generate the prior, but quantum computing can also be applied, as also was mentioned during the first presentation, for solving optimization problems, right? And in case of machine learning, so training machine learning models is almost all about optimization. So have you maybe also used this quantum computing applications for just optimizing some problems to just accelerate the process of training such generative models, or do you think that it can be done with the current infrastructure, with the current hardware?
I think you might really enjoy the paper by Alejandro, which is literally called Quantum Enhanced Optimizer.
Oh, okay.
I mean, the paper isn't called that, but the model is called that, the Quantum Enhanced Optimizer. So I think I don't have an experience for kind of optimizing model parameters with a quantum computer. That's not something that I kind of know about, but like what their paper, like Alejandro's paper very recently, what they do is to kind of find a shared vision, like fusion of optimization and generative modeling. Because I think there is very subtle but strong similarities between these two fields. And as I sometimes think about it, and perhaps you shouldn't, but like this is how I think about it. I personally see generative modeling as optimization is a very strong fit to your data, right? Like you want to find the best example, and generative modeling rather as a somewhat weaker fit that generalizes. And in this like paper of enhancing binary optimization with quantum-inspired algorithm, it really shows that you can train your generative model on previously pretty successful like optimization instances, right? So like kind of samples that had pretty good cost function evaluation. You feed that to your generative model, it proposes new ones, and they like these have better, like they can have like much better kind of the spread obviously goes both ways, right? Like it always also proposes like worse instances, but also better ones that the optimizer never saw. And so they really show that these kind of frameworks of optimization and generative modeling, they might be closer connected than we might think.
Mm-hmm.
So I think Tamer just posted the paper in the chat.
Great.
Great. So yeah.
Thank you very much, Tamer, also for sharing the link. Thank you, Manuel, for explanation. Yeah, a lot of knowledge and fantastic knowledge. I believe that all our participants have learned a lot. So that was really great presentation and discussion. So thank you very much for this. And yeah, I don't see more questions now on our chat. So I think that we can finish for today. So Helen will soon stop recording the meeting, and the recording will be later available on Washington's Meetup channel. So yeah, we would like to thank once again, thank Tamer and Manuel first of all for your great presentations and accepting our invitations.
Thanks for having us
today. Thanks for all the participants. Thank you very much for great questions from your side. I believe that was a very fruitful meeting. Yeah, so let's stay in touch. The next meeting of Washington's group will be in 2 weeks from now. So we hope to see most of you then, and we are looking forward to it. Thank you very much.
And thank you everyone for the questions.
Thank you, Pawel.
Thank you.
Thank you, Tamer. Thank you, Manuel.
Yep.
Have a nice Saturday.
Bye, Terrill.
Bye.
Thank you.
Good to see you all.